For this lab, the motion of a spring which is oscillating in both the x and y directions will be observed. We will look at the motion of a spring in the real world, analyze its motion, and then using physics principles such as the energy principle and Newton's second law of motion, construct a computational model that will depict this motion. We were given the initial conditions of the mass as seen in this picture of mass and also the relaxed length of the spring mass system. Once Professor Greco releases the object, which starts at rest, the force of gravity and the force generated by the spring move the mass in both the x and the y directions as seen here. Now that we have seen the real footage of the mass, we must now construct the model. We will consider the mass moving in both directions, the forces that are acting on the mass, and the energy changes that the mass experiences. Before we dig into the details of the code, feel free to pause the video and thoroughly analyze any section of the code to fully understand how it works. Here we see that the initial conditions of the motion of the mass from the video are correctly inputted into the code. Also, we are going to read in the actual motion of the mass as depicted by Tracker to compare the two models in a couple minutes. Other initializations that are necessary for the code to show the correct movement of the mass include the period of oscillation, the spring's stiffness, the rest length of the spring without the mass, length of the spring when in motion, and the kinetic, gravitational, potential, and spring potential energies of the mass. To find the period of the oscillation, the y position will be used. We will look at a point in time seen here, 6.08 seconds. And we subtract this second time, 1.52 seconds, from the first to find the period of 3 oscillations of the mass, and then finally divide by 3 to find the period to be 1.52 seconds. Now that we have the period, the spring constant can be calculated. Based on our knowledge of angular frequency, we can relate the period and mass of an oscillating spring to be the value seen here. Based on the equation for the magnitude of the force of a spring, we can rearrange the equation to show the rest length of a spring. When the mass is initially at rest and no forces besides gravity are acting on the mass, the magnitude of the force of the spring will equal the force of gravity, and therefore we can calculate the rest length without the mass. The stretch is calculated as usual based on the force of a spring equation. L is calculated to be the position of the mass due to the origin, which in this case is the position of the fixed point of the spring. And finally, the direction of L can be calculated. The energy of the mass can be calculated using the kinetic energy of the mass, the spring potential energy of the mass, and the gravitational potential energy of the mass equations. If we consider the block, the spring, and the earth as our system, the entire change in energy, the sum of all the energies of the system, will be equal to 0 since no outside work is being done on the system. This is true based on the energy principle. Inside the loop, the gravitational and spring forces are calculated based on their force equations. Also, the net force acting on the mass is calculated as the sum of all the forces. Next, Newton's second law is utilized to update the velocity of the mass, and then the position of the mass can be calculated using the second equation seen. After this is complete, the length of the spring is recalculated based on the new position as well as the stretch and direction of the spring. After recalculating the position and velocity of the mass, the energies are once again calculated in the same way as was shown before. These final energies for the time step are used along with the initials that were copied earlier on in the loop to find the changes in the energies and the change in the total energy of the system. And finally, the position of the real life motion are read in every 19 times the loop runs, which is based on the frame rate of the camera. Here we can see that the forces acting on the mass as it moves are the spring force, which varies and is shown in blue, and the gravitational force, which remains constant and is shown in black. The net force is seen in the small yellow arrow. The direction of the net force points toward the position of rest that the mass was in to initialize our code. The motion of the y positions of our model is seen in blue and is pretty close to the motion of the real spring. The model is off by approximately a centimeter here and there, and the error can be due to the misplacement of the mass points on the tracker software. This includes the calibration stick's position and accuracy. The x direction is off by quite a bit, and this is due directly to the calibration stick being slightly off from its perfect positioning and length. What does it mean? Number 1. For our model system, is the energy principle satisfied? As we can see by this chart of all the energies of the system, the yellow line is at a constant 0 value, which shows the total energy of the system. As mentioned earlier, the system is the earth, the spring, and the mass, and therefore no outside work is being done on the system. Therefore, the energy should be 0, and our model does satisfy the energy principle. Number 2. Using the data obtained in Tracker, make 2 separate estimates of oscillation periods. First, by estimating the period of oscillation from the x position data, and second, by estimating the period of oscillation from the y position data. Compare the 2 estimates and discuss. Earlier, we calculated the period of oscillation based on the y direction, and we will similarly calculate the period for the x direction. We get a value of 1.63 seconds for the x direction, which is slightly different from the y direction's period, which was 1.52 seconds. If we plug in this new period into our equation at the same place as we did for the y direction's period, we would see final motion results like this. The model is now much worse at predicting the motion in the y direction. However, in the x direction, the model remains the same. This is because the x direction's period is determined by using the equation of period equals 2 pi times square root of the length of the pendulum divided by the gravitational acceleration. For this reason, any object that is hanging from a pendulum of length 0.7 meters will oscillate at this motion on Earth. For the model we created, we must use the period of oscillation based in the y direction to calculate the correct motion of the mass. In conclusion, we were able to fairly accurately model the motion of a real-life spring based on the initial conditions given to us and using the energy principle and Newton's second law. The error in our estimation is due to the slight misplacement of the original calibration stick on the resting mass. This threw off our motion in both the x and y directions by small amounts. Thank you very much for watching.